Hi, y'all. It's Mrs. Blasky again. Today we're going to go a little bit out of order. We're going to talk about topic 0.6 and 0.8. They go together pretty well. We're just going to skip over 0.7 for right now and come back to it later. So 0.6, balancing chemical reactions. This is something you guys were pretty good at in first year chemistry. Just something that you got to remember that you need to be able to do. Remember that the point of balancing chemical equations is to put coefficients in front of each chemical species that's there to satisfy the law of conservation of mass. Whatever goes into a reaction has to come back out of a reaction. So if you have a certain number of particles coming in, or not particles necessarily, but atoms of each element, then those same atoms need to come back out of your reaction. The number of particles might change. You might take one particle and break it up into pieces. You might take multiple pieces and smash them together into one. But we keep track of that with the coefficients. Those coefficients are sort of like a recipe. They tell us how many particles of each of those chemicals are joining together. Those ratios can also tell us how many moles of each of those chemicals are joining together. So again, hey, look, see this weird dot 12H2O thing? Make sure you know what that means. I'm going to let you guys look that one up. If we take a look at number 2, let's pick something pretty straightforward for right now. I've got aluminum, solid aluminum, plus gaseous oxygen produce aluminum oxide as a solid. There's a lot of information you can get from those equations. Remember about all of our symbols and all those things that can happen. So right now I've only got one aluminum on my reactant side, but I've got 2 aluminums on my product side. So I'm going to put a coefficient of 2 there to make my aluminums balance out. Now when I look at oxygen, I've got 2 oxygen atoms on this side. I've got 3 oxygen atoms on my product side. That's not going to work out in an easy way like the aluminum did. I'm going to have to find a common multiple for that. So if I can get it to 6, I put 3 oxygens here. I put a coefficient of 2 there. That means 3 times 2 gives me 6 total oxygens for the O2. 2 times 3 gives me 6 total oxygens for the aluminum oxide. Now, I changed this coefficient in front of the aluminum. Now I have 2 times 2 gives me 4 aluminums on my product side. I still only have 2 on my reactant side. So instead of a coefficient of 2 there, I need a coefficient of 4. Now, when you write those coefficients, they should always be as simplified down as you possibly can. So if you had, instead of 4, 3, 2, you had 8, 6, 4, technically that is not correct. We could simplify that down. And so make sure you're always checking when you're done. Those coefficients are as simplified as they can get. Again, make sure you know how to do this. If it's something that's pretty easy peasy to you, don't need to practice it a whole lot. If this is something that you struggled with, make sure you practice it. Right? I gave you a ton of example problems on here to practice. Answer key is posted on Schoology, so you can check and see how you're doing. For right now, we're going to skip over stoichiometry. We'll come back to it in a little bit. But let's talk about the different types of chemical reactions. We're going to talk about several different types. Again, AP chemistry is not going to be like when we were in first year chemistry and you just had to identify what type of reaction was. And they gave you lists and you're like, what kind of reaction is this? What we're going to get into is, well, if I know that this is a precipitation reaction, these are the ways I need to handle it. These are the other types of things we can do with this equation. If I see that I have a combustion reaction, what does that mean about what's going on? What else can I do with that? Okay, so for right now, we're just going to identify them. We're going to carry those facts through to some other things later on in the school year. So first type of reaction we're going to talk about is a precipitation reaction. A precipitation reaction occurs when 2 aqueous solutions react to form a solid precipitate. We're going to do a lab in class that talks about this and how to handle those. In first year chemistry, you had a big old list of solubility rules about, well, if it's got this in it, it's soluble. If it's got this in it, it's not soluble. Remember, soluble means to dissolve. In AP, we don't care about all that mess. We care about the 4 most common things that are always soluble. And that is the abbreviation SNAP. S stands for sodium. If it's got sodium in it, it is always, always, always going to be soluble. That's an N. Nitrates. So if it's got the polyatomic ion nitrate in it, it is always, always, always going to be soluble, no matter what else it's bonded with. Sodium has a plus charge. Ammonium, NH4+. It's got an ammonium ion in it, always, always, always going to be soluble. And potassium. Now, it bothers me that potassium is K, but it says SNAP. Bothers me. Potassium, K+, always going to be soluble. If you know those four, we're pretty good. When we have aqueous solutions combined to form a solid, we can simplify down the chemical reaction for that with something that we call a net ionic equation. This is probably the most important thing in this whole first unit 0 that carries through all the way through the whole year of AP Chemistry. And it's the thing that people forget how to do the most. So we're going to spend a decent amount of time practicing this and making sure we know how to do it. So a net ionic equation represents the whole chemical reaction happening, but it does not show the spectator ions or the chemical species that do not change throughout that reaction. Okay. So let's see how we can handle this, how we can figure out what is actually changing and what isn't. So we've got example 34, question number 1. We've got ammonium carbonate reacting with aluminum nitrate aluminum nitrate to make ammonium nitrate and aluminum carbonate. Okay. What we need to do, very first step, we need to take anything that is labeled as aqueous. If something is aqueous, that means it dissolves or is soluble in water. So in water, ammonium carbonate doesn't actually exist as ammonium carbonate. It actually exists as ammonium ions and carbonate ions. So it really is ammonium ions and carbonate ions. Now, let's make sure that we keep these balanced and we keep track of all of the ions that are there. It's got a 3 out in front and a 2 here, so that's a total of 6 ammonium ions, and 3 times 1 gives me 3 carbonate ions. Now the aluminum nitrate, our other reactant, also is aqueous, so it's going to also exist as ions in solution and not as a compound. Aluminum is aluminum plus 3, nitrate NO3 minus. This is why in previous times I talked about it's not so important that you can call that aluminum nitrate, but you need to be able to know what the ions are in it to be able to write it down. Again, we need to make sure that we have the correct number of those ions. I've got a coefficient of 2 out in front. That means I've got 2 aluminums. 2 times 3 gives me 6 nitrate ions. I'm done with my reactants. Now I need to look at my products. My first product, ammonium nitrate, is still aqueous, so that also is going to break up into ions. So same as before, I've got 6 ammonium ions and 6 nitrate ions. But now my aluminum carbonate says solid. So that's not going to break up into ions when it's in a solution. It's going to stay a solid. It's going to be a chunk sitting in the bottom of the beaker. So just because it's a chunk in the bottom of the beaker means it's also going to stay a chunk in my formula. I tend to write solid at the end of that one just to remind myself that it stays together. Technically, every single one of these ions could have the label of aqueous. It takes up a lot of space. It's not necessary. AP isn't going to grade you off by leaving it off, so I tend to not write it. Now, this, what we just wrote, this is called a total ionic equation. Okay. If we want a net ionic equation, we need to look at all of this and we need to see what did not change from the reactant side to the product side. I can look and I can see here's 6 ammoniums, here's 6 ammonium ions. That didn't change from the reactant side to the product side. We call that a spectator ion. So since it didn't change, we can drop it out of our equation. I can also see that 6 nitrate ions did not change from the reactant side to the product side. So those are also spectator ions. I'm going to drop it out of the equation. For my net ionic equation, which is sometimes called NIE, net ionic equation, we only keep the things left over that did change from the reactant side to the product side. So my net ionic equation shows me what actually happened in that reaction, not anything else that's floating around in that beaker that didn't change. So on my reactant side, I've got the 3 carbonate ions, I've got the 2 aluminum ions. On my product side, the only thing I have left over is that solid precipitate. That is my net ionic equation. This is very common on the AP exam. This is something that we've got to make sure that we master. We'll be working on it together. That all goes along with precipitation reactions. Back in first year chemistry, we might have called that a double replacement reaction. It means the same thing. Whole bunch of practice. We're going to work on some of that together. You can do some of it too. Answers are on Schoology. Second type of reaction is a combustion reaction. I think these are the easiest to sort of pick out off a list. Combustion reactions always have something that's got carbon and hydrogen in it. It could have oxygen in it also. Reacting with molecular oxygen, O2, and forming carbon dioxide and water. Combustion reactions are highly exothermic. They almost always create a bunch of energy. This is the reaction that makes your vehicle go. It's what makes engines go. Anything that burns fuel is a combustion reaction. So these ones are pretty easy to pick out of the list. Again, we'll be talking about combustion reactions a lot later on. These last 2 groups also, we will be talking about a bunch later on. Acid-base neutralizations. If you mix an acid with a base, you get a salt or an ionic compound and water. We're going to do a whole unit on acids and bases second semester. But just to be able to recognize that that is a specific class of reaction. We also have something called an oxidation-reduction reaction. 3 different types of reactions that we talked about in first year chem sort of fit into this oxidation reduction. We can have single replacement reactions, where a single element reacts with a compound. One of those elements switches places. We have synthesis, where we have smaller molecules combining to form one larger molecule. And we have decomposition, where we have one larger molecule breaking up into 2 or more smaller molecules. Again, just being able to identify this, we will talk more about what oxidation reduction means and why the oxidation numbers change, but really you just need to think about it's really changing the way that those molecules are bonded. Here, zinc was by itself, now it's forming a bond with another molecule or another element. Here, hydrogen and chlorine were bonded only to themselves, now they're bonded to each other. That's a big change in the way that they were bonded. When we compare that to something like a precipitation reaction, we look at this one we just talked about. Yeah, ammonium changed who it was bonded to, but it still didn't change the way it was bonded. It still was an ionic bond to another ion, okay? So that's why those oxidation reduction ones are so different. After this list of different types of reactions, there's a little bit of practice to be able to identify which type of reaction there is. This is all about looking for patterns. Again, this is not a question that would probably come up on an AP test, but it's something that we need to be able to recognize so that, again, if we know that it's, for example, a synthesis reaction, later on we'll be able to identify different sorts of problems we can answer about that because it is a synthesis reaction. All right. Again, take some time, do some practice, ask any questions you got in class. Let me know how it all goes. I will see you all later. Bye.